Right. So we're going to talk about collisions. So when we're worried about, when we're trying to understand what happens when two things collide with one another, right? There's a lot of complex things that go on during a collision, right? Like if you have a Prius and another Prius, I don't know why I always use Priuses. If you have two cars that collide with each other, there's like parts flying everywhere and other parts ramming at each other at different angles. But the point of the matter is that we can kind of abstract away what happens during the collision. And as long as we know enough about the initial conditions, i.e. before the two objects collided, and the final conditions, i.e. after the two objects collided, we can understand a lot of what happens, or a lot of what the results of the aftermath of the collision are, without actually going into the nitty-gritty of what happens during the collision. So it is true that on the other hand, that the nitty-gritty of what happens during a collision that will affect. It does not affect momentum conservation, right? Maybe it's might be some Freudian slip. My mom had a Prius growing up. Anyway, but momentum conservation, or momentum is conserved almost always, right? As long as we're just considering two bodies colliding and there's no external forces on them, momentum is conserved. But and that doesn't care about what's going on during the collision, what types of forces are present. However, it's not necessarily true that mechanical energy is conserved. Remember, mechanical energy is kinetic energy and potential energy. But if during the collision there are some internal non-conservative forces, like things grinding against each other and so on, that could affect how much of the initial energy becomes thermal energy. So just as a quick recap, if the collision forces, whatever those might be, are springy, i.e. like a spring, like a spring between the two blocks, then the forces are conservative. Then we have conservative forces during the collision, and that implies that we call these elastic collisions. And that's for obvious reasons, right? If, on the other hand, if the collision is frictional in nature, think the example that I gave last time was you had one book sliding onto another book. This one has some initial velocity, this one doesn't. That is technically a collision, right? Initially they weren't interacting, then they interact and now their speeds are different and there's some other result. There's some end product. You could consider that as a collision. So just like in that example, then we do not have, not conservative forces. Then we have non-conservative forces. And so we call those inelastic collision. So basically, all collisions are inelastic except the ones where every single force involved is conservative. So you might say, okay, well, how do you actually deal with these collisions? What are we trying to understand? Well, it turns out that the two different cases, elastic and inelastic collisions, have different equations that are associated with them for good reason. If a collision, I should specify, almost always momentum is conserved. So if a collision is elastic, that means there are only conservative forces, then energy is also conserved. And what does that do for us? Well, that gives us an additional equation to use. Now, when I say an additional equation to use, what I'm getting at is that the typical collision type problem that you might be asked to solve, whether in this class or in the real world, is two things collide, or maybe three things collide. What is the speed and direction that part, or that thing B or thing C or thing A leaves the collision with? And so there are some variables that you're going to have to solve for using algebra. And the more equations we have, the more variables we can solve for. So the fact that we get an additional equation because energy is conserved, i.e. we get energy initial equals energy final, that's an equation that will involve our variables, that allows us to solve for more things. So elastic collisions can often be easier than inelastic collisions to handle. Let me give a quick example here. So let's say that before the collision takes place, we have a block of mass m moving with speed v, and there's another block of mass m moving with no speed. It's not moving at all. Then we have an elastic collision, where the two blocks collide with one another, and there's collision happening. And then afterwards, we have a block with mass m, speed v, and another block with mass m moving off. Now, it turns out, if you were to actually solve this problem, say what are the final speeds of each of the blocks, you would find that the incoming and outgoing speeds are the same. The question is, why? So let's do our first application of momentum conservation and energy conservation. So there are no external forces here. We're going to consider our system as both blocks. So that means that we get momentum conservation as usual. And so what does that say for us? That gives us that the momentum before, and this is a one-dimensional problem, so we don't have to worry about the vector symbol, is equal to the momentum after, which is to say that we have the formula mv plus 0. So we have the mass of the first block times its velocity, plus the mass of the second block, m, times its velocity, 0. That's just mv plus 0, that's the momentum before, is equal to the mass of the first block times the velocity of the first block after the collision, plus the mass of the second block, which is also m, times the velocity of the second block after the collision. We can rearrange this to get v equals v1 plus v2. So here's one equation that we have access to that comes from momentum conservation. Similarly, the collision is elastic, so we can do some more algebra with the other condition. That is, the initial energy is equal to the final energy. Now, in this case, there's no potential energy anywhere in the problem. We're ignoring gravity, there's no springs. So all we have is the kinetic energy before is equal to the kinetic energy after. So what does that imply? That implies 1/2 times mv squared plus 0, that's the kinetic energy before, is equal to 1/2 mv1 squared plus 1/2 mv2 squared. This is the kinetic energy of the second block after the collision. This is the kinetic energy of the, sorry, that was the first block after the collision. This one is the kinetic energy of the second block after the collision. And so again, we can rearrange, and we get that v squared, which is the speed of the first block, is equal to v1 squared plus v2 squared. So that's our second equation. Okay, now we have two equations. Now it turns out that this is precisely what we need. We were looking for the final speeds of both blocks. We don't know what they are, they're v1 and v2, but now we have two equations and two variables, so we can solve. So let's just substitute in v is equal to, let's substitute this in here. So I'm going to work with these two equations. So we have v squared is equal to v1 plus v2 squared, but that whole thing is equal to v1 squared plus v2 squared, right? So we can FOIL this out. We get v1 squared plus 2 v1 v2 plus v2 squared is equal to v1 squared plus v2 squared. We can cancel off a whole lot of things, and we're left with 2 times v1 v2 equals 0, which tells us that one of them is 0. So v1 equals 0 or v2 equals 0, and then from this first equation we get that the other one is v. So this happens a lot in collision type problems where you'll get 2 solutions. So why is it? So why can both of them be valid? Like why did, like, they collided? Why is it that there are 2 possible outcomes? Like only one thing happens. So the key here is that we didn't actually put information into the equations that tell us that they collided, right? For example, if mass 1 had missed the block, i.e. it kind of just sailed on by, that also would be technically an elastic collision, right? There's no external forces, and there's a, all I did was I substituted this equation into there. So imagine instead of them colliding, imagine that this one had sailed on and passed this one. So then afterwards it would just pass right over. Well, that's technically an elastic collision because there are no external forces, and there's no and all internal forces, all 0 of them, are conservative. So these equations these equations that we've written down are equally well satisfied for both when the first block strikes the second block and when the first block misses the second block. So if you consider the case where the first block misses the second block, that would be the case where v2 just stays 0 and v1 just stays its initial velocity, v. Whereas if the first block strikes the second block, then you must then get the other option, the option where v1 becomes 0 and v2 becomes v. So that's why there are 2 solutions, because we actually couldn't distinguish with our equations which of those 2 situations happened. And so you have to be careful. Sometimes the problem, like when you're reading a problem or something, the problem will indicate which of the solutions are sensible to take for what it's asking. Let's work out another example. By the way, these are one-dimensional collisions that we're looking at. Let's say before we have a block of mass 2m with speed v, and it hits a block of mass m. This is very similar to the previous one. So by the way, and then we have an elastic collision. They collide. And then we have after, we have the block of mass 2m, and maybe it's moving to the left or to the right. Let's just assume it's moving to the right, and if it's moving to the left, it'll have speed negative. It'll have a negative velocity. And then m, certainly the block of mass m is moving to the right, though. So what are those values? What are v1 and v2? So we can solve that. We have enough data. We have precisely 2 equations. One of them is momentum conservation. The other is energy conservation. And so that'll give us 2 equations, which is enough to solve for the 2 variables. I'm not actually going to go through it because these are perhaps good examples for you guys to work out. Another example. Before, maybe we have a block of mass m moving with speed v to the right, and then a block of mass 2m that's stationary. And then they have an elastic collision. As usual, I'm just drawing this for your sake, but you don't actually have to draw these. And then after, maybe the block is now moving to the left, and this block is moving to the right. But again, if our initial assumption was wrong, all we would do is we would get a negative value for this v1, if instead it was actually moving to the right. It turns out that the arrows that I've drawn are correct, and you can work that out for yourself. And by the way, it's not the case that you're always given initial information and you try to find the final information. It could be the other way around. Maybe, and actually this is in the homework, maybe you're only given information about what happens after the collision, then you can use that to almost backtrack through the collision and figure out what happened beforehand. Figure out what the initial speeds were, say. So if it wasn't clear, by the way, from last lecture and from earlier, the total momentum of a system is just equal to the momentum of each part, which is equal to the sum of the mass, the total mass, times the center of mass velocity. That's just a useful feature, and that's how I'm solving all of these. I write down the total momentum of the system before, the total of the momentum of the system after, and then I just set them equal to each other. And the way I write those down is just by adding up the momentum of each part. Now, there's another type of collision. We talked about elastic collisions. Now we have to talk about inelastic collisions. And actually, give me just 1 sec. Want to make sure that I have enough. Yeah, okay. All right, so now we need to talk about, does momentum have a direction? You have a vector. Yeah, momentum is a vector, right? I dropped all of the vector notation here because we were only doing one-dimensional motion, right? Remember when we were talking about one-dimensional motion at the very beginning of the course? We could just talk about x rather than the position vector r. But in general, all of those equations that you would have had for one-dimensional motion with just x, we replace with a vector. And so the same happens here. And we'll get to multi-dimensional, like more than one, like collisions in multiple dimensions later, or actually just like in a minute. But yes, every energy is a scalar. Energy is just a number, but momentum is a vector. It points in the same direction as the center of mass velocity. Because it's just mass times velocity, and velocity is a vector. So there are 2 types, or 2 varieties perhaps, 2 varieties of inelastic collision. The first type is perhaps you are told how much mechanical energy is lost, or maybe that's something you solve for, is lost. And it's lost, by the way, it's not like gone into the ether, it's lost to thermal energy, i.e. it just becomes, some of that mechanical energy gets transformed into thermal energy. So you're told how much is lost during the collision. For example, the external work, which is always 0. This is the change in kinetic energy plus delta PE, which again, in our case is usually 0, plus there's some change in thermal energy. Yeah, that is an example of thermal energy. And so this delta, this is the, momentum is almost always conserved. As long as there are no external forces, momentum is conserved. This delta E thermal is the amount of energy loss. I'm going to put that in quotes because it's not actually lost, it's just transformed. The second variety, so by the way, in this first variety, you still can use a form of energy conservation. It's just instead of having 0 equals delta KE, you have 0 equals delta KE plus delta E thermal. And then if you know delta E thermal is, say, 8 joules, then instead of having KE initial equals KE final, you have KE initial equals KE final plus 8 joules, right? Say plus delta, or minus, I suppose, minus delta E thermal. No, that should be plus. The point is you take, if this delta E thermal tells you how much energy is lost to thermal energy, then you just take your final kinetic energy and add that much energy to it to get your initial kinetic energy. And then it's just like solving an elastic collision. It's just your energy conservation equation is slightly different. And so then you would follow everything through. You still use momentum conservation, you use this new energy conservation, and then you solve for everything in the same way. So the second variety is called totally inelastic. It's a totally inelastic collision. So this type of inelastic collision occurs when the two objects become attached. I.e. stuck together. Think like throwing two hunks of mud at each other. They're just gonna, like, or two hunks of clay, if they'll come together and they might keep moving, but they're gonna stick together, they're gonna stick to each other. So while you cannot use energy conservation in that case, I mean, you could, but it's not easy to solve. We do have another equation. In fact, we have that the final velocity is the same for both objects. So just like how we needed two equations to find the two variables, the two final velocities, now we have, it's not an energy conservation equation, it's just say v1f equals v2f. That's a perfectly valid equation. It's just an equation of a different form. Come on. So let me just jot this down. The idea being that you still have the same number of equations, so you can solve for the same number of things. It's just we have a different type of equation. And that's enough. As long as you have, so you always have momentum conservation, almost always. Basically, anytime you can disregard any external forces, then you have momentum conservation. And so each of these three cases, elastic collisions, inelastic collisions, and totally inelastic collisions, all of them provide you with one additional equation. So they're all equivalent in the sense that in all three cases, you can solve for the same variables. You just might have to, your last equation might be different. In the first case of an elastic collision, it's just standard energy conservation. In the second case of a not totally inelastic collision, it's like energy conservation, but there's some extra stuff thrown in. And then in a totally inelastic collision, you don't have energy conservation at all, but you do have this equation where you have v1f equals v2f. And so as long as you have the correct number of equations, you'll be able to solve. And from there, it's just a matter of writing down your equations. If you'd write down, and these are all in one dimension, of course, you'd write down equation 1, equation 2, solve for your two variables, and then you're done. So collisions in one dimension aren't particularly difficult. Collisions in two dimensions, not that much more difficult either. They take longer. So I'm gonna quickly go over collisions in multiple dimensions. I.e., it's not necessarily a head-on collision, maybe it's some sort of bouncing off, something like that. So let's say that, let's just work with an example. As usual, it's important to give a coordinate axis. Let's say we have a block or a ball of mass m1 moving with speed v. So let's say before we have a ball of mass m1 moving with speed v to the right, and then we have a ball of mass m2 with speed equals 0. And then they collide. So by the way, just for reference, the momentum in the x direction here is just m1 times v, right? Because there is no velocity in the y direction here. And the momentum in the y direction here is 0. Sorry, this comes from the fact that the second ball isn't moving. This comes from the fact that neither ball is moving in the vertical direction. So then there's some sort of collision. And so maybe we have a first ball collides with the second ball in some way, something like that. Maybe it's an elastic. Well, I'll generalize and then we'll see how it pops out afterwards. And then afterwards, we have maybe a ball over here going off with some speed v2. We have a ball over here going off with some speed v1. And then from the horizontal, we might measure these, we might measure these angles. This might be theta 2. This might be theta 1. It's just some way of characterizing the direction that they're going. And the reason we're measuring relative to the horizontal is just because it agrees with our coordinate system relatively well. So then, what is the momentum in each direction? Well, the momentum in the x direction is the x component of the momentum of the first ball plus the x component of the momentum of the second ball. And so we have to figure that out. Well, what is the x component of the momentum of the first ball? So px1, well, it's always just the mass of the ball times the velocity in the x direction. In this case, that velocity would be v1 times cosine of theta 1, right? And I'm going to assume, by the way, that theta is measured from the horizontal. So this would actually be a negative value. And similarly, the momentum in the y direction would be v1 sine of theta 1. So I'm going to write out the total momentum. This would be m1 v1 cosine of theta 1 plus m2 v2 cosine of theta 2, right? That's just it's the mass of each object times its velocity in the x direction. And then similarly, we do the same thing in the y direction. m1 v1 sine of theta 1 plus m2 v2 sine of theta 2. I made this whole point about theta being measured or theta being negative if it's going down, just to make sure that the signs all agree here. Oh, actually, for consistency with my notes, no, actually this is fine. So then what do we have? Is momentum conserved in any type of collision? Yes, it is conserved in any type of collision, as long as there's no external forces. I mean, momentum is conserved always as long as there's no external forces. So if you just consider your system to be large enough so there aren't any, then you're good. Right, so then what is the momentum conservation? Momentum conservation gives us the following equations. It gives us, in the x direction, that m1 times v, because that's the momentum before in the x direction, is equal to m1 v1 cosine of theta 1 plus m2 v2 cosine of theta 2. Gravitational energy in this y direction, no, so I'm not considering gravity here. If you wanted to include gravity, then you could, but I'm not considering that. Perhaps this is viewed top down, so you're seeing two billiard balls hit. In the y direction, we have 0, because that was the initial momentum in the y direction, is equal to m1 v1 sine of theta 1 plus m2 v2 sine of theta 2. Okay, so those are two equations that we have so far. And then let's see what pops out if we assumed this was elastic. If this was an elastic equation, then we have 1/2 m1 v squared. That's the initial kinetic energy, because only the first ball is moving. And that has to be equal to the final kinetic energy, which is 1/2 m1 v1 squared plus 1/2 m2 v2 squared, right? If it's inelastic, let me move this over just a smidge so I have more room. Well, then what do we have? We can still use the energy conservation. We just have to add however much E thermal was lost to the right-hand side. We have 1/2 m1 v squared equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus delta E thermal. So, and so you would pick one of these, whichever one is relevant to your problem. So all that happens when we get into more than one dimension is, well, first of all, if you have two objects, you can always imagine that they're colliding in a plane. You never have to worry about a third dimension as long as there's only two objects. So the whole point here is that all this is just a slightly more complicated version of the one-dimensional collisions. You just have one more equation, and you have a few more variables. In this case, you have two more variables for the angles that the objects go off in. And that means that you'll actually need more information to solve these, right? You need to know maybe you need to know something about, I don't know, the relative angle between the two. So let's actually put this on pause for a minute and derive a nice well-known result in 2 dimensions, or for elastic collisions. So suppose we have an elastic collision where the masses are the same. Have a 2D elastic collision where M1 equals M2. Okay, that will simplify our equations a little bit. But so recall here that kinetic energy is equal to momentum squared over 2m, right? That's just a fact that I hope you guys remember. I derived it Monday, here. It's just a way of relating momentum to kinetic energy rather than having to work through velocity. Basically, you take the momentum, you take the velocity, you rewrite it in terms of momentum, and then you just plug that back into kinetic energy and you get this out. So if that's true, then energy conservation, which holds because this is an elastic collision, the energy conservation equation is the following. It is p squared over 2m, that's the initial energy. This is equal to p1 squared over 2m plus p2 squared over 2m. This is the momentum of the first ball, the momentum of the second ball. And I didn't call it m1 and m2 anymore because they all have the same velocity, or they all have the same mass. So then we can rearrange this, or simplify, to get p squared equals p1 squared plus p2 squared. So this is our first equation that we get from energy conservation. Now remember, all of these p's, these are actually vectors. So if I wanted to be precise, I would put vectors and magnitudes. So this is a statement about the squares of the magnitudes. But remember that if I write this is the same as p dot p, and we often just shorthand it to just p squared. So you kind of have to know from context what objects I'm talking about. But we're talking about a 2D collision, so momentum should be a vector. Okay, so I should actually keep that up as a recall. Recall that p squared is defined to be p dot p. That's what the dot product of a vector with itself is just the square of the magnitude. So what does momentum conservation give us? Momentum conservation, again, always holds. So momentum conservation gives us the following equation. It gives us that the initial momentum, p, has to be equal to the sum of the final momenta, p1 plus p2. That is precisely initial equals final. And initially, the initial momentum was just equal to the momentum of the ball that's just moving. We're imagining this case here, by the way. The first ball is stationary, or the second ball is stationary, the first ball is moving towards it. And by the way, you can always work in a reference frame where that's true, right? If they were coming at each other, you could just work in the reference frame where this one is stationary and then this one will have the speed of the two added together, right? So you can always do this. Right, so we have this as our momentum conservation equation. So what do we have? Well, why don't we substitute this into this equation? So our first equation was p squared, and so let's substitute in that is equal to p dot p. But that's equal to, from this equation here, that's p1 plus p2 dotted into p1 plus p2, right? And that's all supposed to be equal to p1 squared plus p2 squared. But right, and we'll get to why that's true in just a minute. So this is just a way to calculate p squared, and so we can FOIL this. So we get p1 dot p1 plus p1 dot p2 plus p2 dot p1 plus p2 dot p2. And so this is just p1 squared because it's a vector dotted into itself. Then we have 2 times p1 dot p2 plus p2 squared. Sorry, I don't need the vector symbol over it if it's squared. Okay, great. Now, so we have this equation here. That's just, that comes from momentum conservation. We haven't used the energy conservation yet. And so combining it with the energy conservation, that p squared is equal to p1 squared plus p2 squared, we can simplify. So with the energy conservation equation, we get that p1 squared plus p2 squared equals p1 squared plus 2p1 dot p2 plus p2 squared. All right, now we can do some canceling. So we're left with 0 equals 2 times, well, we can do some even more canceling, is equal to p1 dot p2, right? The dot product between the two momentum vectors is 0 if they have the same mass and if one of the balls was initially at rest. So what does that mean? Well, remember that the dot product between two vectors can be written as the magnitude of those vectors, the product of the magnitude, times the cosine of the angle between them. It does mean they're orthogonal. That's precisely the point. And so as long as p1 is not 0 and p2 is not 0, that means that we have that cosine of theta equals 0, which implies that theta is 90 degrees. The interpretation being that if you have two masses, one of which is initially stationary and the other is moving with some speed, and they have the same mass, as long as the masses don't collide head-on, which we've already handled, in that case, one of the balls stops and the other one keeps going, then they ricochet with an angle of exactly 90 degrees. i.e., if we have a ball going and then hitting another ball, then the end result is the two balls come off at a right angle to each other. Which is kind of remarkable, right? Like, it's like it doesn't matter, like, if one ball hit another ball at like a slight angle, they will always come out perpendicular to each other. It doesn't matter how they hit each other as long as it's not head-on. The reason why we can use that, why we can't use the argument when it's head-on, is because when that's true, one of these will be 0. In fact, it's the first momentum is 0, in which case the first ball doesn't even move, so it doesn't make sense to measure the angle. So as an exercise for you guys, let's do the same thing, but let's do not the same thing. Let's do another type of example. We have a totally inelastic collision, and it's in 2D. This is also easy to deal with because what we have here is we have momentum conservation as usual. We also have that, by the way, that implies pi equals pf. We also have that final speeds are the same. That gives us another equation, v1f equals v2f. So the example here is maybe before you have a ball of mass m1 moving with some speed v1. You have another ball of mass m2 moving with speed v2. And then after, you have the two balls stuck to each other, moving maybe at some velocity, vf, at some angle relative to the horizontal. And so in fact, if you were given all of the information about v1 and v2, you could find both the angle and the velocity because those are two variables, and we have three equations. So you could actually find even more, because indeed, yeah, we have three equations here. We have the momentum in the x direction, the momentum in the y direction, and the well, and we have I guess that's four equations, but it's not really, because all that just says is, well, okay, I guess we have four equations, but we also have three unknowns because you could have imagined that you have theta1 and theta2, but the fact that theta1 and theta2 are the same is kind of assumed. So the point is you would just go and you would solve, and you have plenty of information. So that's more that hopefully that's more than enough about collisions. And there's two of the homework problems are about collisions, and there's a whole bunch of resources about collisions if you guys need more help. But I'm just going to go through and do some standard examples that you'll see, one of which is closely related to one of the problems that you'll see on the homework about collisions. So here's a classic example. It's called the ballistic pendulum. That's a terrible E. So the ballistic pendulum is basically, you have a block of wood or jelly or whatever hanging from, say, of mass capital M, hanging from the ceiling, and then you shoot a bullet at it. Maybe the bullet has mass little m, and it has some initial speed v. Afterwards, the bullet becomes lodged in the mass in your block, and now the block has mass m plus little m. And what's going to happen is it will swing up some amount. So maybe the question is how high does the pendulum swing? Well, there's a trick to this type of problem, and this is what you're going to have to do on the homework problem. The trick is that during the collision, the collision is completely inelastic or totally inelastic. And the reason for that is because the bullet gets lodged in the block of wood or block of jelly or whatever, and so they start moving together. They have to move at the same velocity. During the swing, we have energy conservation. So during the collision, energy is not conserved, right? Because it's totally inelastic. But during the swing, energy is conserved. And that's just because there's no external forces, right? And well, the only external force is gravity, and gravity is a conservative force. So energy would be conserved in that case. So what you do is you break it up into two parts. So the first part would be you would figure out the final speed of the two combined block, or of the block combined with the bullet, before it starts swinging. So it would hit, and then it would have some speed, right? And so you use that, you solve for that speed, knowing that the collision is totally inelastic. And then from there, you can compute the initial kinetic energy of the block plus bullet with that speed, and use energy conservation to figure out how high it has to swing by converting that kinetic energy into gravitational potential energy. And that will let you compute how high it swings. So it's kind of a two-part problem. You break it up into during the collision, or before the collision, right after the collision, before it starts swinging up, and then after it's reached its max height. And you use two different problem-solving techniques in those two parts, i.e. before the collision and right after the collision. You use collision mechanics, basically, momentum conservation, and that they have the same final velocity. And then right after the collision, to how high it goes, it's just energy conservation. Another classic example, and I wish I could actually show you this, but I can't do this demo here. Actually, maybe I can. I have one rubber ball. Do I have another rubber ball? Yeah, I do. Maybe I can show you this. All right, I'm going to take off my headset. but you guys aren't saying anything anyway. All right, so 2 rubber balls. Let's see if. So the idea is that I could take these 2 rubber balls, drop them, and then when they hit the ground or hit something that's firm, the idea would be that one of them would be launched really high, the other one would not. This is not going to be very visible. Let's see what I can bounce this off of. Maybe something like this. No, actually. So A, this is not a very bouncy thing, and B, these balls have to be of different mass, otherwise it won't work. I'll explain it instead, and you guys can Google this problem. It's actually really amazing when it happens, especially if you're seeing it live. And I've demoed it live, and I've managed to hit the ceiling of the Rossler lecture hall by dropping them from, shoulder height. But unfortunately, I can't do that because the camera's bad, and But the point is you start with it's this problem with stacked balls. And so before, you have a ball, a larger ball, and they're both falling together at some speed v, and they hit the ground. And then something happens in the middle, and then what the larger ball is moving up with some speed because it bounced off the ground, and then the smaller ball is moving up with a different speed. The question is how do those speeds relate to each other? It turns out that there's actually several collisions that happen here. And you can Google how to do it. I don't want to give away too much, but basically the first, or the smaller ball bounces off the larger ball more than once. Think of it as there's a collision, they're together initially, then the first ball compresses a little bit before the second ball hits it, and then it gets bumped up by the larger ball. And so it transfers a lot of its momentum. And if you stack enough of these balls, this process repeats over and over again. So almost all of the momentum and energy of the bottom balls is all transferred into the smallest ball, and so it goes really high. It's really cool. Last classic example is Newton's cradle, and you've probably seen these toys in doctor's offices. Newton's cradle is basically, it's this toy where you have a whole bunch of balls sitting, and then if you lift up 2, it makes 2 more go. If you lift up 3, it makes 3 more go. You guys know what these things are. And then it does something like this. One question that you might ask is, how does it know to send up the correct number of balls, right? Why isn't it that it just sends, if you send 2 balls in, why doesn't it just send up 1 ball twice as high? And the key here is that these are all elastic collisions, so it puts constraints on the mass of the object that it launches off. And so you could actually work out these collisions, and again, I highly recommend that you look up this derivation and try to understand how it works for yourself. That it has to be the case that the right number of balls go up, because the mass of the incoming and outgoing have to agree. It's a neat derivation. I'm not going to go into it because I only have 2 minutes. So that's basically it when it comes to collisions and linear kinematics, which is what we've been, or linear motion and Newton's laws that doesn't involve rotation. That's basically it. I would have liked to have covered this material by Monday, but unfortunately we didn't have enough time. We're a lecture behind. No, material from this lecture won't be on the midterm. And not much of the material from lecture 1 will be on the midterm either. But yeah, so we are a little bit behind. We'll have to catch up at some point. Right, but that's all I have. I suppose I will end it there, and I'll take questions. How hard will the midterm be? You realize that that's an impossible question for me to answer, right? I don't know how hard you'll think it is. I think it's sufficiently easy to be done in 50 minutes. But you guys probably won't agree. How should you review for the midterm? Well, hopefully you've already been reviewing. You should be doing practice problems. You should make sure you understand the homework problems 100%. And once you're there, or if you don't, go find more problems on the internet. Khan Academy has a whole bunch of really good ones. No, collisions will not be on the midterm. Khan Academy has a whole bunch of great resources. Google, just in general, will have a lot of, all right, so people have asked what's on the midterm. Go check out the course schedule. It will tell you what's on the midterm. Yeah, and the difficulty will be approximately the same as the homework. Yeah, but shorter problems. Are there any collisions in the real world that are truly elastic, or is that an ideal scenario? Yeah, it's an ideal scenario. Really, so this whole business of inelastic collisions, every collision is inelastic. Well, okay, actually, let me rephrase that. There are some. So collisions don't have to just be two objects colliding, right? Collisions are just when any two bodies come in, or initially are not interacting, and then interact and then do something else. So magnets might be a great example. If you threw two magnets at each other in space, that would be completely elastic. Or maybe you have two objects that are gravitationally attracted but slightly askew. They'll like swing by each other. That is an elastic collision. How will the midterm format work? Well, we just need to scan a piece of paper that we use to do our work on Gradescope. So I sent out exam instructions. Everybody should have checked those already. And if you have questions about the exam instructions, like how it works, send me an email so I can update the exam instructions. Please, everybody look at that. That is super important. Like I will not be able to answer questions about how the exam works because I'm not proctoring the exam. Other TAs are. So you need to make sure that you understand exactly how it's going to work. If you don't, then you're going to be out of luck. Yeah, I will be recording the review session I'm holding later today. Oh, let me stop recording here.